Howdy. This video is on Le Chatelier's principle. Le Chatelier's principle is a powerful general concept that will help you understand how systems respond to changes. For example, changes in volume, temperature, or pressure. It's easier to understand and apply Le Chatelier's principle than to try to memorize a lot of other stuff. It's a very powerful tool. After watching this video, you should be able to determine how a system will respond when it's at equilibrium and then the concentrations of products or reactants changed. You should be able to determine how a system will respond when it's at equilibrium and then the volume of the container is changed. And you should be able to determine how a system will respond when it's at equilibrium and then the temperature is changed. So Le Chatelier's principle says that if a system is at equilibrium, meaning Q equals K, and it is disturbed such that Q no longer equals K, the system will counter the disturbance to get back to equilibrium. Another way of thinking about it is, we can describe a reaction using this plot, and the most stable configuration is down here. And so another way of thinking about the Chatelier's principle is that if the boulder is on the bottom and you push it up, the darn thing just rolls back down. If you push it up again, the darn thing rolls back down. The boulder always ends up at the bottom. We don't know how long it takes, but always ends up at the bottom no matter where it starts. And so things that might disturb a system at equilibrium would be adding reactant or product, removing reactant or product, changing the volume of the reaction chamber, changing the temperature. Now notice that for these first three, they might change Q. And so you have to actually look at what is the expression for Q and see if Q has changed. For example, if you're looking at a solubility of an ionic solid going to aqueous ions and you add more solid, that does not change Q because pure solids, pure liquids are not in reaction quotients and equilibrium constants. And so if we add silver chloride to water, the sum of the silver chloride will dissolve, forming silver ions and chloride ions. The economic expression, we have silver ion concentration times chloride ion concentration. And so we add a little silver chloride. Once we get to that minimum, where Q equals K, no more silver chloride will dissolve, no matter how much more silver chloride we add. And the reason for that is that the silver ion concentration times chloride ion concentration equals KSP is the most stable configuration for this system. So what happens if 1 mole of silver chloride is added to water? Well, enough will dissolve until we get to Q equals K, or until the silver ion concentration times chloride ion concentration equals the KSP, which is 1.8 times 10 to the minus 10th. And then the rest will just remain solid. So what happens if the chloride ions are added to a saturated solution of silver chloride solid at equilibrium? So saturated solution means you're down here at the minimum. And so the question is, you're at the minimum and you add chloride ions, say like sodium chloride, which is very soluble. What will happen? Well, once you add the chloride ions, you'll increase Q, right? Q is going to be silver ion concentration times chloride ion concentration. You add chloride ions, that increases Q. And then more silver chloride solid will form to reestablish equilibrium. So again, at equilibrium, you're down here. Again, you can think about a boulder in a valley. Adding chloride ions is like pushing the boulder to the right, and then the boulder just rolls back down. And again, this is just an example of Le Chatelier's principle. The system is reestablishing equilibrium by consuming some of the added chloride ions. What happens if you're at equilibrium and more silver chloride solid is added? Well, silver chloride solid is not in your equilibrium expression, so it does not change Q. So even after adding the silver chloride solid, Q still equals K, and so the system does not respond. And so here we have a different reaction. Iodine gas plus hydrogen gas forming hydrogen iodide gas. And so if the system's at equilibrium and then more iodine is added, does that make Q greater than K, less than K, or equal to K? So Q is here. And so if we add iodine gas, Q will get smaller, and so Q will be less than K. And so again, it's like a boulder. By adding the iodide, we're pushing the boulder to the left. How does the system return to equilibrium? Some of the added iodide will be consumed, forming HI. So you push the boulder to the left, the darn thing just rolls back down. And so here we have a graph, the log concentration versus time. And so here we're at equilibrium. Concentrations are static, but you still have the forward reverse reaction. It's just that their rates are equal. We add iodine gas, and that bumps that up. And then some of the iodine gas is consumed. You're also consuming some H2 because this reaction is going forward. And you're producing hydrogen iodide, and that's going up. Now, if you take these concentrations and you plug it into this expression for K, and if you plug in these concentrations into K, you get exactly the same number. The system is just returning equilibrium. And so we added iodide, and then some of that iodide gets consumed until we get back to equilibrium. And again, this is just an illustration of the Chatelier's principle. The system reestablishes equilibrium by consuming some of the added iodide. If the system's at equilibrium and some H2 gas is removed, does that make Q greater than K, less than K, or equal to K? And so if we remove H2, that means Q will increase. Notice that K is a constant for a specific reaction at a specific temperature, so K will not change. But if we remove H2, Q will increase. And so again, we're at equilibrium. Remove H2, and Q goes up. And so we're taking the boulder, pushing it to the right, and the darn thing will just roll back down. And so how will the system return to equilibrium? We've removed some H2, and so HI will produce some more H2. All right, so if we're here where Q is greater than K, products form reactants until we get back to equilibrium. And again, here we have the concentrations. Here we're at equilibrium. We remove some H2, and then what happens is some of the removed H2 is made. And we also make some I2 because the reaction's going to the left until we reestablish equilibrium. And so if we take these concentrations, plug it into this expression, we'll get a number. If we take these concentrations, plug it into the same expression, we'll get exactly the same number. And so again, this is an illustration of the Chatelier's principle. The system reestablishes equilibrium by producing more H2 after some had been removed. So the system's at equilibrium, and then the volume is doubled. Does this make Q greater than K, less than K, or equal to K? Now, K is independent of the volume, and so we're just looking at how will this change Q. And so if we look at it, we got two gas particles products, two gas particles reactants, and so actually Q will not change. And so if we're not sure about that, we can do a little math. And so Q is, the partial pressure of H2 squared divided by partial pressure of I2 times partial pressure of H2. Now PV equals nRT, so P equals nRT over V. So we can plug in this for our P's. And then notice that the RT's cancel, the V's cancel, and we end up this way. Now, the RT's cancel, the V's cancel, just because we have the same number of gas particles on either side. And so if you have the same number of gas particles products as reactants, then changing the volume will not change Q. And so the system will remain at equilibrium. And so when the total pressure was changed by changing the volume, Q did not change because the number of gas particles, products, or reactants was the same. So here we have a different reaction, 2NO2 going to N2O4. if the system's at equilibrium and then the volume is doubled, does this make Q greater than K, less than K, or equal to K? Now in this case, we have one gas particle product, two gas particles reactant. And so if we double the volume, do you think we want to make more gas particles or fewer? So doubling the volume, we'll want to make more gas particles. And so if we double the volume, that should push the reaction towards the left. And so again, we can look at Q, do some math. And so Q is, P N2O4 divided by P N2 squared. P is nRT over V. We plug that in. And we see that because we do not have the same number of gas particles, products, reactants, only one of the R2s cancel, only one of the V's cancel, and so we're left with that expression. And so doubling the volume actually causes Q to increase. So Q depends on volume only because we don't have the same number of gas particles, products, and reactants. And so because Q increased, that means products will form more reactants, like I said initially. So again, if you have more gas particles, reactants, and you increase the volume, more reactants will be produced. If you have more gas particles, products, and you increase the volume, more products will be produced. If you have more gas particles, reactants, and you reduce the volume, the system will want to go to less gas particles, and so products will be reduced. If the system's at equilibrium and then the total pressure of the system is increased by adding neon gas, does that make Q greater than K, less than K, or equal to K? Now in the previous question, we had changed the pressure by changing the volume. Here we're adding neon gas. Notice that neon gas is not in our expression for Q, and so that will not change Q. Adding inert gas, neon gas is a normal gas, will not change Q. And so if Q and K remain the same, then the system remains at equilibrium. So changing the pressure does not change the value of the Eckman constant temperature. Solids, liquids, and aqueous compounds are not affected by pressure changes. Changing pressure by introducing inert gas will not shift an equilibrium. Only when there's a change in the partial pressure of gases that are part of the equilibrium will the system respond to the equilibrium pressure change, as long as Q is no longer equal to K. If there's equal number of gas particles as products and as reactants, pressure changes due to changes in volume have no effect on the system. So again, please remember, a system only responds if Q is no longer equal to K.
The molecule nitrogen dioxide is unusual in possessing an odd number of electrons. The Lewis structure shown here is one of several that can be written for NO2, which exists as a brown gas. Nitrogen dioxide reacts with another NO2 molecule to form colorless dinitrogen tetroxide, in which the odd electrons on two molecules pair up to form a new nitrogen-nitrogen bond. In the gas phase, an equilibrium is established between NO2 and N2O4 molecules. The equilibrium lies heavily toward NO2. When the volume of the system is decreased at constant temperature, the overall pressure increases. Suppose that we were to halve the volume instantaneously. Here is a graph of the pressures of NO2 and N2O4 as a function of time. Notice that when the volume is instantly halved, the pressure of each gas is instantly doubled in accordance with Boyle's law. After this instantaneous decrease in volume, the system is no longer at equilibrium. Le Chatelier's principle tells us that the chemical equilibrium will shift in a direction that partially undoes the effects of the volume decrease. That means it will shift in the direction of more N2O4 to undo the doubling of the pressure in the system. The pressure decreases as more N2O4 is formed because the total number of molecules decreases. On our graph of the gas pressures, we see that the decrease in NO2 pressure is twice as large as the increase in
N2O4 pressure. And so again, the Chatelier principle, the entire concept is that the system will respond to counter the effect. And so if you're reducing the volume, the system goes to the side with the fewer gas particles from right to left. So if there's 1 bar of NO2 at equilibrium in a sealed container, what must be the partial pressure of N2O4? And so we can use the Eckham expression. We have PnO2O4, partial pressure of NO2 squared equals our K of 6.82. And so we're told that the partial pressure of NO2 is 1. 1 bar squared is 1. And so we get that the partial pressure of N2O4 should be 6.82. If 1 bar of NO2 and 6.82 bar of N2O4 are at equilibrium, and then the volume of the container is reduced by a factor of 2, changing the partial pressures to 2 and 13.6, what will be the partial pressure of NO2 and N2O4 after the system returns to equilibrium? So initially we're at equilibrium. We calculated these numbers, and then we're reducing the volume, and these are our new partial pressures. Now if we plug in these to our Eckham expression, we will not get 6.82, so that tells us we're not at equilibrium. Now we can figure it out if we start with our reaction, and so we have our initial change equilibrium, so our ice table. So initially we had 2 bars after the change in volume, and 13.64 bar. Now when 2 of these react, we'll form one of those. And so initial plus change gives us equilibrium, so 2 minus 2x, 13.64 plus x. Now our Eckham expression, we have products of reactants, coefficients become exponents. And so we plug in the 13.64x for the partial pressure of N2O4, and the 2 minus 2x for the NO2. Remember, that gets squared, and that equals 6.82. Now, we're going to have to multiply this out, and so we multiply both sides by this term, we get that, and then we multiply throughout here, and we do some algebra, subtract 13.6 from both sides, subtract x from both sides, we end up with that, and so we end up with a quadratic equation. And so for the quadratic equation, we can solve that using this formula. And we end up with, remember, for the quadratic, you always get 2 possibilities because you have that plus or minus. We have 1.018 or plus or minus, or sorry. So the answer is this plus or minus that, which gives us 1.75 or 0.2855. Now, if we think back about what x means, and so our x has to be less than 1, otherwise the concentration of NO2 would be negative. And so that first one cannot be the answer. And so again, when you do the quadratic equation, you'll always get 2 answers. One will not be possible, and so it must be the other one. And so we plug in that value for x that we found, and we get our new partial pressures, plug them into our expression, and we get our equilibrium constant like we saw before. So initially we had this, and then we have the volume, and so it immediately took the pressures up, doubling them, and then eventually these got back to equilibrium. Now if we take these partial pressures, plug them into our Eckham expression, we get 6.82. We take these partial pressures, put them in our Eckham expression, we also get 6.82. Now again, reducing the volume always goes to the side with the fewer gas particles. And so after we reduce volume, NO2 formed N2O4. So we're looking at the same reaction, and so increasing the pressure by decreasing the volume shifts the equilibrium towards the side that has a smaller number of gas particles until concentrations and partial pressures are consistent with Eckham expressions. Now this reaction is exothermic, meaning heat is a product. And so if the system's at equilibrium and then the temperature is increased, will more products or reactants be produced? And will the Ekman constant be larger or smaller? So remember, the Ekman constant is a constant for a specific reaction at a specific temperature. Changing temperature often changes the Ekman constant. And so heat is a product. And so if we increase the temperature, that's like adding heat, that's going to push the reaction to the left, and you'll produce more reactants. The Ekman constant is products of reactants. If you increase the number of reactants, the amount of reactants, you'll decrease the Ekman constant. And so by raising the temperature, we're going to produce more reactants. And so higher temperature will mean smaller Ekman constant for exothermic reactions. It's just the opposite for endothermic reactions. For endothermic reactions, higher temperature means larger Ekman constant. For exothermic reaction, higher temperature means smaller Ekman constant at higher temperatures. And so for this reaction, we see that at 0 degrees Celsius, Kc equals 1299. At 25 degrees Celsius, it decreases to 169.
When NO2 is placed in a closed cylinder under pressure, it reacts in part to form N2O4 molecules, and an equilibrium is established. The formation of N2O4 from NO2 is an exothermic process. Thus, heat is emitted when two NO2 molecules form an N2O4 molecule. The reverse process, dissociation of N2O4 into NO2 molecules, is an endothermic process. Le Chatelier's principle predicts that when the temperature of the equilibrium system is increased at constant volume, the equilibrium will shift in the direction that absorbs heat. This means that more N2O4 molecules will dissociate as the temperature increases.
And so again, higher temperature will push this reaction to the left, consuming some of that heat. And the Chatelier's principle, again, it's very helpful. It's very powerful. It tells you that if a system's at equilibrium and then it's disturbed such that Q no longer equals K, the system will counter that disturbance. So again, if you think about gases, if you reduce the volume, the system will go to the side with the fewer gas particles. If you have an exothermic reaction and you raise the temperature, the higher temperature will mean more reactants. So things that might disturb the system at equilibrium, adding reactant to product, it might change Q, as remember, pure solids, pure liquids do not appear in reaction quotients or Ekman constants. Removing reactant to product might change Q, changing the volume of the reaction chamber. And so if you have the same number of gas particles, products, reactants, changing the volume will not change Q. Changing temperature will probably change K, not Q. Remember, K is a constant for a specific reaction at a specific temperature. I hope that helped.